candidate at the University of Nevada, Reno. If you are watching this video, you likely missed me at LPSC or want to revisit my work or just keep up with my progress. So this is this is a recorded poster similar to the poster talk I'm giving at LPSC 2023, which is in Houston this March. And so essentially what I'm doing with my work and is wrapping up the work I've done on 2 drill core from Hawaii. These cores are part of a project to characterize subsurface alteration pathways on Mars, funded by the Solar Systems Working Grant. And we are going to be focusing on looking at revisiting these samples and using infrared spectroscopy on varying scales and what that can tell us about the alteration. And so quickly, as a side note, if you are new to my work and want to learn more, I have archived all of my research abstracts and presentations on my personal website, which is pujashivam.com. I also have blog-style research notes that break down my fieldwork as well as methods I've used, and then an archive of, again, all those research abstracts, recorded presentations, literary resources, and as well as PDFs of my posters and my presentations as well. So a quick introduction of what my work is. We are investigating the mineralogy of deep drill core from Hawaii as subsurface groundwater and aqueous alteration analogs to Mars. For those in the planetary community, we are well rehearsed in the evidence of secondary minerals forming in the subsurface and then being exposed predominantly by cratering or other weathering processes. This poster is actually going to be focusing on the characterization of minerals using spectroscopy at varying scales and how that might inform the way we explore the surface of Mars. So what I mean by various scales, we are cross-examining the results of bulk and high-resolution data in both the short and long wave. The bulk short wave, which is going to be right here, was a field collection using an in situ handheld instrument with a spot size that's roughly the size of my thumbnail. And so you can see a visual representation of that. And that is just looking at the drill core that was pulled from the underground. More bulk data was collected in the long wave by crushing the samples and sifting them to ensure grains were larger than 125 microns. They were packed into these plates and analyzed by a Nicolet FTIR instrument. And the sifting was to ensure that larger grains because dust particles can cause multiple scattering, and we wanted to avoid that. And then I'll explain why a little bit later. And then we investigate the samples in high resolution. These are going to be in thin section and in billets. And so the high resolution methods were scanned where spectra was collected at a pixel with these scales. So the short wave was a bit of a larger scale than the long wave. And I want to show you this image. I really like this one because it shows you the fine grained nature of basalts. And so this is one of my basaltic samples, and you can just see how fine grained the ground mass is. So just keep all of this in your head as we progress through the poster. I will start with the bulk spectroscopy. In the short wave, first we take spectra down core. So these are, you'll see depths, and those are depths below the surface from where it started. So in the short wave, we take spectra down core, mainly targeting the alteration. We sort the spectra by depth, assigning the spectra to a pixel, and then elongating that pixel so it looks like you're looking at a core. And then this allows for spectral manipulation and representation using a special software called ENVI. So the left side shows the N numbers that we have here that characterize common minerals in each core. We are grouping them based on their mineralogical, so their geologic grouping, so phyllosilicates, sulfates, mafics, and then have the software identify which pixels have those spectra that we've identified. This really speeds up the process, especially when you have upwards around 700 spectra to analyze. And so in the PTA core, we mostly have zeolite and phyllosilicate signatures, which you can find here. in the core, and then which indicates a neutral pH environment that may have been warmer. The KMA has this widespread jarosite feature, right here in the visible, and many other sulfate and hematite signatures. There are also some instances of phyllosilicates at the bottom. And so you can see that visual representation here, and it kind of shows you any patterns, especially in the KMA where it's really focused on the center, and then the PTA where you have a zonation of sulfates kind of in the middle here. So now in the long wave, which is going to be over here. So due to the nature of data collection, these samples, if you recall the last photo, were mixed, right? So we utilized a linear mixing model. This is a simple Python code that takes the collected spectra, compares it to a spectral library I curated. So I took around 28 minerals from the USGS and JPL labs. These are pure mineral end members of various mafic and secondary minerals we were confident that were going to be in a sample, and as well as blanks. So blank spectra that accounts for opaques and oxides, as well as albedo effects. And then this model tells us what percent of each mineral is in that collected spectra. So this is not much quantitative, rather than like a bulk characterization. And so we plot those results as a bar chart to show you kind of what those spectral contributions were. And it gives you an idea of the variation down core, how we can detect feldspars, olivines, where those at, where the pyroxenes are, where the clays are, where the sulfates are. So moving on to the high resolution method, so we have now taken the samples. We've taken the samples in the field going down the geocore. We take some samples back, crush them, and do the long wave. And then we also send a portion of those samples to be made into thin sections. These thin sections come back as flat surface billets. So these billets are about a centimeter thick, and it's just rock that's sawed flat and embedded in epoxy. And then we also receive the actual glass thin section, so like a plate. And the high resolution scans on the shortwave were done by Bethany Ellman at Caltech, where there was it's basically a 200 by 200 micron pixel. And then the long wave, I went to Stony Brook and used Tim Glotch's, it's like a high resolution Nicolet FTIR scanner, where the pixel sizes are 50 by 50 microns. And so for this particular side, I just want to show you the spectral M members of the high resolution shortwave scans. Although there were more N members identified than the bulk shortwave scans, just by slightly more, they were largely consistent with the spectral we were actually gathering in the field. So a lot of it did not veer. We did include and find one other mineral N member, like carbonates, but it was in one sample, so it was not found elsewhere. But other than that, almost all of the N members were the same than the ones collected in the bulk. Now with the long wave, we are making distinctions where we have upwards around 19 N members, and this is largely due to the fact that we are still able to have pixels with mineral mixtures, even at that high resolution scale. And they're going to make up a large part of the spectral gathering and data in that long wave. So I have examples for both mafic and secondary minerals. So for the mafics, because feldspar and pyroxenes make up the most of the fine grained ground mass for these basaltic samples, we would make N members not just on the depth of these absorption features, but also the slight shifts that you have because there might be some diopside mixed in with labradorite, if that makes sense. The secondary, but also to add, there are variations and shifts in absorption features for feldspars because of twinning. There can be zonation in a lot of these mafics, and so it was important for us to distinguish that and make sure that they got their own grouping. And then I provide secondary mineral examples. Here we have carbonate, and then we also have quartz as an example. So for the carbonate, we were confident that this collected top blue spectra was a grain of carbonate, And then we just took spectra of the pixels as we left that grain. And so the rim of the grain with the ground mass, and then just outside the ground mass. And so you can see how that progresses slowly. And then we group it as a carbonate and then carbonate mixtures 1 and 2. The same goes for quartz. Quartz was a little bit harder to justify. We decided a quartz clay mixture because many clays just have a single peak in the long wave. And so that was a lot of the characteristics that we saw. And so we chose a place where we knew that quartz was within a clay vein, and then through SEM imaging, and then we were able to target that in the long wave and get a really good quartz spectra, and then get those subsequent clay mixture end members. And we grouped it. Again, it was harder to justify, but we agreed upon these few features over here indicating that yes, there is quartz in this sample. And so to wrap up this cross-examination, I provide you an example of one of our samples and it provides you all the data combined. And so that you can visualize it all in one place. So I'm going to start with a shortwave on this left side, where in the bulk, we just get a clay mineral signature. So if you just took this data, you would be under the impression that the basalt is altered into a phyllosilicate. Because the peaks are very strong, you might be under the impression that this is heavily altered or that the phyllosilicate makes up most of the sample. However, in high resolution, we will see that this is not necessarily the case. Not only do we additionally detect zeolites on top of the clays, we can see where they are forming, which is around these bugs, which were likely going to be maybe olivines that dissolved and now left this bug space, or a bug space that was there in formation and then got infilled by the clay. And we can also see that much of the ground mass is a mafic response, and they are well preserved throughout the sample. Now, in the long wave, we have this single spectra that has been collected from the crushed sample that is a mixture of clays, zeolites, and mafics. However, in the high resolution scan, you can really characterize that ground mass, which are mostly mafics that are dominated in this rock. This suggests that alteration is not as widespread as we originally perceived. So now, how do we translate this for the way we explore Mars or even other planets? I think it's important to emphasize that spectroscopy is a non-destructive method. And so this cross-examination reveals that both bulk and high-resolution methods have great uses, and they're very valid techniques for mineral identification. We demonstrated, even though the mineral identifications agreed with one another, we were also able to get more information rather than it disagreeing. We were able to build on the information that we had. So the high resolution methods are particularly useful compared to the bulk because basalts are very fine grained, and it's difficult to characterize that ground mass unless you have a high resolution method. And even then, we still, even at the highest resolutions, we were still encountering mineral mixtures. So bulk data can be analogous to the way we receive and interpret remote sensing data, so stuff collected by satellites. And those high resolution methods may inform and kind of are analogous to the way we collect and analyze samples in person, whether it is going to be those Mars return samples coming back or even meteorites. With that, I just want to thank you all for listening. I'm sorry I missed you at LPSC, but I hope you got a lot out of this, and feel free to check out my website. Should you have any more questions about my work, feel free to contact me via email as well.